There are other continuous distributions of interest, in particular the gamma distribution. Here, instead of waiting for the arrival of one event, as in a Poisson process, using the exponential distribution, you might be interested in the amount of time it takes for, well, R events to occur. So the wait time for that is a generalization of the exponential distribution. We call it the gamma distribution. The relationship is a little bit the same as the one between the geometric discrete distribution and the negative binomial distribution. The number of trials until a success occurs, the number of trials before R successes occur. So the gamma distribution has the following probability density function, and you will see that if R is equal to 1, it reduces to the exponential distribution. Okay? So it's probability of having to wait less than 0 units of time would be 0, and the probability of having to wait more than 0 units of time, so the probability, say, of having to wait y units of time, then that's y to the r minus 1 divided by r minus 1 factorial times the lambda rate, which is basically the rate for one such event, e to the minus lambda 1. Now, you cannot express the cumulative distribution function with the help of elementary functions. So our hope of having a CDF, which is simple, as was the case with the exponential distribution, is not actually met. But we can see whatever the true form of the CDF is that the expectation on that waiting time is simply R times the expectation for one event, because there's R such events. So that makes sense. That's compatible with what we've seen for the exponential distribution, and that the variance would be R times the variance for one arrival, rather the variance for the wait time one arrival. So R times 1 over lambda squared. Well, as an example, let's say that you know that on average 30 customers per hour arrive at a shop following some sort of Poisson process. So you have a lambda. The lambda would be half a customer on average every minute. Here we're making the decision that the unit of time will be the minute, one of them. So what's the probability that the shopkeepers will wait more than 5 minutes before both of the first two customers arrive? Well, you're basically computing the probability that y should be greater than 5, and y is the random variable that denotes the wait time in minutes until the second customer arrives, which means, according to what we've seen, that it follows a gamma distribution with parameters 1 over 2, that's the lambda, and 2, which is the r, the number of customers. Now we know what the probability density function for that is. It's this expression right here. Y to the r minus 1 divided by r minus 1 factorial times lambda to the r times e to the minus lambda times y. So all we need to do again is to replace lambda by 1/2 and r by 2 in the expression. And I'm reminding you that we're computing the integral of this function between 5 and infinity. If you were to draw the gamma curve here, 1/2, 2, this is your 5. You are interested in the probability that the random variable will draw a value in the area to the right. Well, that's the area under the curve from 5 to infinity here, if you're waiting for 5 minutes or more. And so you have to compute this integral. I'll simplify the expressions at first. So just do the arithmetic and you will find that the integral that you're computing is the integral from 5 to infinity of y e to the minus y over 2 divided by 4 with respect to y. And this is an integral that you can solve by parts. So you do integration by parts. I'm not showing you how to do this. This is something that I'm expecting you to know how to do from calculus. This is the antiderivative of y e to the minus y divided by 2 You multiply by 1 over 4 because we are dividing by 4 here, and you evaluate the antiderivative of both limits, subtract the lower one from the upper one. Well, in this case, what happens when y goes to infinity? This term goes to 0, this term goes to 0, so you're left with minus 1/4 times, replace y by 5. This is the expression you get, about 28%. Does this make sense? Or 29%, I should say. About 29%. Does this value make sense? Well, on average, you get 30 customers per hour. So about 1 customer every 2 minutes. Okay? So on average, you would expect then to get 2 customers every 4 minutes. And this is sort of compatible with this. You know, you're going to get instances where you get more than 2 customers in the first 4 minutes. And sometimes you'll get less than 2 customers in the first 4 minutes. And the fact that you're looking for what happens after 5 minutes, 29%, if on average you get 2 customers in 4 minutes, that sort of makes sense. Here's another example. Let's say that telephone calls would arrive at a switchboard, a given rate of 2 calls per minute on average, and that these arrivals follow a Poisson process. That part's important. If it doesn't follow a Poisson process, then the probability of waiting a certain amount of time for a certain number of successes will not follow a gamma distribution. You can't really do anything with that. But if it does follow a Poisson process, well, and y is the waiting time until the 5th call arrives. What's the probability density function? What's the mean and what's the variance of y? How long would you expect to wait until you get your 5th call? Again, we replace our lambda by 2 and our r by 5 into the formula for the 2-5 gamma distribution, and we get a PDF of lambda to the r times y to the r minus 1 divided by r minus 1 factorial times the exponential of minus lambda y. So lambda by 2, r by 5 throughout. This is what we're going to get right here. So we can just use the formulas for the expectation and the variance. This is r over lambda and r over lambda squared. It's called the gamma distribution because you can extend the factorial in the PDF here by something called the gamma function. So if r turned out to not be an integer, if r was some positive number but not an integer, you can replace r minus 1 factorial, the denominator in the PDF, by gamma r. And gamma r is just the expression that you get here. It's an exponential. It's going to be a function of r because you're integrating with respect to t. And this basically plays the role of the factorial for non-negative integers. The exponential distribution and the chi-squared distribution, which we'll talk about later when we talk about the F distribution, these are special cases of the gamma distribution. So the exponential distribution is a gamma distribution with parameter lambda when r is equal to 1, and the chi-squared distribution on r is basically a gamma distribution with a lambda fixed at 1.